We had this viscoelastic model that took as inputs things like the location of the source, location of observation points, the time of the observations, and so on, and calculated outputs that we wanted to know, strains, stresses, displacements, and so on. And we wanted to essentially find an equivalent neural network that could do this same mapping from inputs to outputs quickly, efficiently, reliably, and on any device. So neural nets may be very familiar to some of you and less familiar to others, so I always spend, I always give a 2-minute overview of fully connected networks. There are many more complex architectures, obviously, for these networks for other types of problems, but these simple, fully connected networks work really pretty well for these two applications that I'll talk about today. So this is my 2-minute overview. So you often see neural nets presented this way, where the circles are individual computational units, or neurons. And in these fully connected networks, they're arranged in successive layers. So there are 4 interior layers in this toy network here. The layer on the far left in red corresponds to the inputs to the network. So in our case, these would just be the same inputs we'd feed into the viscoelastic model. And the layer on the far right corresponds to the outputs. So in our case, these would be the same, or these would be the predicted outputs of the outputs of the viscoelastic code from the neural network. In terms of what each individual neuron does, they each perform a super simple operation. This one in red, for example, it takes as inputs the outputs from the previous layer, weights them relative to one another, performs a weighted sum across them, adds a single value b called the bias, and then it applies a function to that resulting value. And that function is usually something really nonlinear, like a ReLU or a hyperbolic tangent. And that resulting value is then spewed out as one of the inputs to the next layer of neurons. And the goal of working with these is to iteratively tune the weights and biases associated with every neuron until the outputs of the network closely approximate the true outputs of the code, the viscoelastic model. So to do this in practice, we first generated a large training data set that just consisted of sample code inputs and associated outputs. And then we implemented these networks with Keras, running on top of Theano, I think, for this. And we withheld 10% of the data for validation during training. In general, for this application, we found that networks with more than 10 layers and more than 10 neurons per layer tended to do best on the validation data. And a mix of ReLU and hyperbolic tangent activation functions also seemed to perform best. This kind of surprised me, because if you sort of read blogs, it seems like it's ReLUs all over the place, especially for image classification. But for some reason, the addition of the smooth hyperbolic tangent activation functions really helped with performance.
Can you give me an idea of the dimensionalities involved here, like how many input nodes there are?
So I'll talk about this later, because we sort of build it up slowly. But our eventual sort of biggest test case was 6 input nodes and 3 outputs. So we were predicting displacements, and we were inputting. I'll talk about it later, but I'll talk about the different parameters that we trained over. And then, once we found a network that worked well in the validation data, we tested it on a completely independent set of code runs. 2 of the things that were kind of interesting about this, or are slightly different from your kind of classic machine learning problem, I think, that I didn't really appreciate because it was my sort of first time working on this kind of thing. There's no noise at all. So overfitting wasn't as much of an issue for us as I think it is in a lot of machine learning applications, because we didn't have to worry about overfitting to noise. And the other thing was, we had total control over our training data set, and that's not true of a lot of machine learning applications. So we didn't experiment too much with this at all, but it's kind of interesting to think about the fact that with this we can totally choose our training data. So this is a very simple example of what the process looked like. What's shown here in the top left are the x displacements at the surface for a point source at 5 kilometers depth in an elastic half space. So this is a classic Okada point source solution. And the neural network approximation of that same field is in the top right, and the residuals are here in the bottom left. So it's really pretty abysmal in terms of how it's predicting the true output of the Okada solution. But this network has only been trained based on the data highlighted in black. And as you feed in more training data, the neural network's able to reproduce the Okada output better and better. And with only about 1,000 training data points, it's very hard to tell the difference between the two, the true solution and the neural network approximation of the same field. What's sort of neat about this is when you compare the amount of time it took to produce these two solutions, the original Okada calculation takes about 2.8 seconds compared to the neural network. Once trained, the neural network can closely approximate that same output in 1.7 seconds, which is a speed up of 1.5, which is not all that great in the scheme of things.
One string.
Sorry?
One string, you said the right thing.
One string?
You gotta add the training time.
One string, yep. Yep.
Well, you should add it there.
Why? I mean, I
Because
guess
that is time.
it is time. It is time, but it's upfront time, and it's time you only have to spend once.
So
Yeah. But I guess our sort of interest in this is that once trained, it's super fast. So the more you use the network, the more that time pays off. So whether this is worth it totally depends on your application and what you're interested in doing. Sorry?
Writing the code takes time too.
Yeah,
so-
that's true. It all takes time.
No, I
Yeah.
meant on the other side, on the Okada side, you had to write that down.
Yeah.
And figuring out the equations.
Figure out analytically the solution.
That would be great.
Right.
You would have done it.
And we also tested this on a much, much larger scale viscoelastic test case. So here's where the dimensionality comes in. So we trained these networks over the horizontal position of the observation point at the surface, the time after the event, the depth of the earthquake source, and then the Maxwell and Kelvin viscosities of lower viscoelastic half space beneath an upper elastic crust. And you can see this is just a very small slice of the testing data set, but the network performs still very well across this much larger scale test case.
I'm still confused. The input is just a location, and then the output is the displacement?
Yeah.
So the model, the elastic model is fixed, and all this is for one Earth model?
Well, no, so this is for a viscoelastic model, and we've trained over viscosities of the lower crust and upper mantle. So we can feed in those two parameters.
All right, so you have
Yeah.
a two-parameter model
Mhm.
plus the coordinates of the output.
Yep,
Or the-
and the time and the depth of the source.
Yeah.
What's neat about, what was sort of exciting to us about this was, as we added more parameters, it was sort of unexpected. We actually, in order to get the same performance, we could sample more sparsely across each of the parameters and still get the same accuracy, which made me think that this could be very generalizable, because as you add more parameters, you can sample more sparsely. You don't have to just keep building your training data set up to be just enormous.
And are the orientation, is the orientation of the source changing, or is it the
No,
same-
it's not.
Same source?
It's the same source. It's a strike slip
Same-
source.
Same source, you're hearing the depth of this.
Yeah, yeah, yeah. And yeah, and one thing, we didn't think of at the time, but would have been, we really should have taken advantage of some of the symmetries and change, but we didn't do that at the time. We sort of did it brute force for this. The performance of the network across a sort of wider swath of the testing data set is down here. So each curve is the performance as a function of time for different source depths. So we perform about, yeah.
I'm sorry.
No.
And you're sampling from the numerical simulation?
We're
Or how the data which are sampled come from what?
from the code. So
Yeah.
we
And
choose.
that's solving a linear equation, or?
No, it's a viscoelastic model. It's semi-analytic, uses the correspondence principle to solve for sort of viscoelastic stress change and displacements due to both elastic and subsequent viscoelastic relaxation.
The differential equation?
It's
You said semi-analytic, so no. I'm not-
yeah, it's in the Fourier domain,
Okay.
and it's based on the mathematics of Fukuhara and Matsura, sort of solving the equations, writing once you put things into the Laplace domain, you can write viscoelastic equations in the form of elastic equations. But what was really, what we were sort of most interested by in this was that when you compare the amount of time it took to produce the large-scale testing data set with the viscoelastic original code, it took about 400,000 seconds, about like 4 to 5 days. And once trained, the network can come up with a close approximation of that same output in about 6,000 seconds, or an hour and 40 minutes. And then accelerated on a GPU, that same forward performance or forward prediction could be done in about 700 seconds, or 12 minutes, I think. And that's a speed up of over 500, which is really pretty significant.
One question.
Yeah.
How much time do we need to spend on generating the training data?
Yeah, I mean, it took a while but we had already done it for because we'd been working with the code for so long. So we had a lot of training data ready to go. I think it was probably about a month on a single, about a
Because
month.
I see the lead code using such a big number of times. So if you want to create some training set, then you may need, if you use this code, then you may need
Yeah, it takes a lot of upfront cost, but at the same time, once you have done that, you never need to do it again. Yeah.
So when you validate the problem, do you consider when you validate the problem, do you consider the validation data like in the set, as an interpolation kind of?
Yeah.
So you're not going to extrapolate?
Yes. Yeah, exactly. And that's actually something really interesting to look into going forward. We sort of looked at that. Our sort of goal was to just accelerate the existing code, and so we could sample over the whole domain we were interested in. But looking forward, I think it would be cool to see if we could do better extrapolating. I haven't looked into that, so that's a good question.
So one forward modeling run gives you the displacement as a function of x, y, and t. True?
Yes.
And then you're running that for different z's and viscosities.
Mm-hmm.
So how many z's and viscosities were there?
I think, so the training data set was about, 19 gigabytes in total. And I think we sampled, I can't remember the exact numbers. I think it might have been, it was sort of 100 times 20 depths and 100 by 100 grid for XY. It did a really pretty impressive job interpolating.
Yeah, so this is an interpolator over that
It is,
grid
yeah.
solution.
Mm-hmm. Yeah, a very large scale
Fancy.
interpolator. Yeah. Yeah.
Can you estimate, let's say, how many points in each dimension you can find parameters? How many points in each dimension you in average?
When we were training, in terms of the training, it was roughly 100. It depended on, it was for depth. I sampled more sparsely, and I didn't. It was sort of an interesting application, as I said before, because you could choose your training data, and sort of the training data I chose at the beginning worked so well that I never changed it. But it's interesting to think about how we could have sampled things more cleverly, like perhaps sampling very sparsely when the solution isn't changing very fast in time and stuff like that. I think we could have sped things up that way.
Okay, so I understand correctly that in each dimension approximately you have at least 100 points?
That we trained on, yeah. In X and Y, in Z I think we only had 20 or 15. And then, in viscosities we only trained across 5 or 6, I think. Yeah, I'm thinking of X and Y more than, because those were the ones that most of them sampled.
And that's going to be related to the resolution that you want coming out.
Yeah. So once trained, we didn't, this all suggested to us that there's no reason why an even more general network couldn't be trained that could take as inputs all the inputs to the viscoelastic model and come up with close approximations of the outputs. And once trained, all that you need to run these is like 50 lines of MATLAB and Python in a small data file. So with only those 2 small files, you could run very large scale model runs on a laptop in hours or minutes. The other thing that we found kind of, yeah.
Sorry. So you just varied the depth, right? You didn't vary the amount of slip on the patch or the orientation of the patch.
Yes.
I have a question. I don't know about how this exactly works, but in terms of inversion, when you use Okada solutions, they get very much non-unique when you start varying the orientation of the fault. So you can end up with a very similar displacement distribution for two very different orientations. Is this capable of dealing with it?
Well, so we're doing just the forward modeling problem here. It would be interesting to see if it could distinguish between things like that going the other way. But this is just the forward modeling. So we fix the orientation and then predict what the displacements are going to be for this. But that's interesting to see, think about. We also sort of enjoyed thinking about this from kind of a more zoomed out and maybe philosophical perspective in some ways. So this is a visualization of one of the best performing networks on the validation data. So the colors here represent the sign and magnitude of the weights and biases associated with every neuron and connection in the network. So in some ways, the information in this visualization is kind of a new way to write the viscoelastic model. It's a kind of new way to map the code inputs to the code outputs. And so it's kind of interesting to think about, in addition to potentially accelerating these kinds of calculations down the line and maybe enabling them on larger scales than previously possible, these kinds of approaches may also be able to provide sort of insights into the physics involved. And it's kind of exciting because it really could be applied to any type of physical model. So,
Is the oscillation in density
Yeah.
from, is that,
so that,
was it understood?
well, so that, well, I haven't looked into it all that much, but I always assumed, and I think this is probably true. So we had this mix of hyperbolic tangent and ReLU activation functions, and ReLUs sort of don't saturate. They just, it's just y equals x for positive x. And so I always assumed that, the weights, when you multiply, you probably want to have smaller weights when you have that activation function, whereas hyperbolic tangents, saturate. And so that, I think that oscillation is due to that. And I don't know.
Alternated ReLUs and the hyperbolics?
Sorry?
Alternated. You're saying you alternated it across the layers?
Yeah. And I don't know why the hyperbolic tangents helped the performance, because in general it seems like those are older activation functions that people don't use as much anymore. But maybe it was because, I don't know, we were trying to learn a smooth function or something, yeah.
What about the persistence of connections that sort of run from the bottom to the top?
So that,
And in the dense layers, you can see there's sort of a
these
backwards
really
yeah,
dark
yeah.
ones? Yeah, I don't know. The one thing that I found, that sort of insight that I found kind of interesting, and this is a very simple one, but you can see these last two neurons here. Those are the viscosities of the lower crust and upper mantle. So you can immediately get this insight that the weights connecting those to the rest of the network are less than an order of magnitude the size of the weights connecting the rest of the inputs. So you can immediately sort of see that those inputs, changes in those inputs have less than an order of magnitude influence on the final solution as compared to the rest. So it's kind of fun to look at and try to make sense of.
Could you have just
You're
trained
gonna
it?
draw that on the neurons. Try to find the pattern.
Yeah. Sorry.
Could you have trained on the full wave field as one output rather than individual points?
Well, it's quasi-static. Oh, you mean strains and stresses, or?
Well,
The
you have
full-
displacement, let's say, whatever it
Yeah.
is, as a function of x, y, and t.
Yeah.
Could you, for one set of viscosities, could you just say match this whole wave field?
Across all, you mean have it predict
All
a
X, Y.
continuous distribution of?
Yeah, adjust the weight so that you're matching
But you'd have to
your
pick.
complete solution.
Well, so you'd have to pick discrete XY points.
Well,
for
they
it
still
to-
have to be discrete, but you do them all at once instead of one point at a time, as one.
Yeah, I
Where's
mean,
an
you'd have to, it's a
equivalent?
lot more sort of free parameters to.
Well, same
Yeah.
weights, because the same weights ultimately are.
Well, it's sort of equivalent because you input all the X's you want to know when you get
So it
all
is
the
a-
X's you out
Yeah,
you want
this-
to know.
it
Yeah.
is equivalent.
Yeah, let's see.
Yeah, you think
Sorry, I
about
didn't quite. Yeah. Okay, cool. So with that, I'm going to switch gears totally. Well, not totally, and talk about some more recent work that we've been doing that's focused on aftershock location patterns. And I always show this figure from King et al. 1994. This is the Joshua Tree earthquake. And the main shock, the fault that ruptured during the main shock is in white here, and the white dots are the aftershocks that took place in the vicinity in the month after the event. So we were we got interested in this problem of explaining aftershock locations from a machine learning perspective specifically, because one, there are a lot of data about aftershock locations. And then there are also these very well established empirical relationships that can describe aftershock frequency decay over time and aftershock likely maximum magnitudes. But aftershock location patterns have proven a lot more difficult to explain. And maybe the most widely used criterion for explaining aftershock locations is the Coulomb failure stress change criterion. These are the colors in this King et al. Figure. And under this hypothesis, you'd expect that regions with negative Coulomb failure stress change values might have suppressed seismicity, whereas regions with positive Coulomb failure stress change values due to the main shock might have enhanced seismicity. And so Coulomb failure stress change has been successful in a lot of different cases, but there have also been some cases where it seems to not be quite so successful. One of the sort of most, I think, widely known cases is this paper by Hardebeck et al. 1998, where they showed that for the Northridge earthquake, the static elastic Coulomb failure stress changes couldn't explain aftershock patterns significantly better than it could explain sort of sets of randomly distributed events. So we were interested to sort of to take another look at this problem, and we decided to frame it as a binary classification problem to make it kind of tractable from a machine learning perspective. So if you have a toy fault here, then we can grid up the area around the fault into grid cells, and then sort of frame the problem as trying to classify each grid cell as either containing or not containing aftershocks. And so once you've established this framework, it's easy to sort of assess how well you're doing at discriminating between these two types of grid cells using well-established tools for binary classifiers like ROC curve analysis. So these may be very familiar. I hadn't really worked with them before, but they're very common in machine learning and in the medical literature. So the true positive rate is plotted on the y-axis and the false positive rate on the x-axis. So if you had a binary classifier that was much better than random assignment in terms of its discriminating ability, it would have an ROC curve that looked like the red curve. Whereas a binary classification scheme that was no better than random assignment would have an ROC curve that looked more like the blue curve, close to the 1-to-1 line. I often, Uden's index, the specificity plus the sensitivity -1, which is the maximum vertical distance that this curve reaches, is sort of a nice metric that takes into account both kinds of misclassifications equally. And the area under the curve is also often used as kind of a bulk performance metric. So this can be extended easily to 3D. So this is a slip distribution from the Landers earthquake taken from the source mod catalog of finite fault rupture models. And we can grid up the volume around this fault into 5 kilometer by 5 kilometer by 5 kilometer cubes. And then, so these are the sort of cubes in the vicinity of this Landers slip distribution that contained one or more aftershocks in the year after the event. And so once the volume around the slip distribution is discretized this way, we can then use the slip distribution itself to calculate static elastic stress changes at the centroids of each grid cell, and then try to use those static elastic stress changes to classify the grid cells as either containing or not containing aftershocks. And a lot of the literature, not all of the literature, but a lot of the literature around Coulomb failure stress change and aftershock locations is based on 1 to 3 main shocks and their aftershocks. So we really wanted to build as large a data set as we possibly could. So we used, I think, 118 distinct main shocks from the source mod database, and that actually consisted of 199 slip distributions because there are multiple slip distributions contributed by different authors for earthquakes like the Kobe earthquake in Japan. For each of these slip distributions, we sort of discretized the volume around them and then took all of the earthquakes that occurred within 100 kilometers horizontally in every direction and down to 50 kilometers depth from the ISC catalog. So we assembled sort of, I think, so in total it was over 160,000 aftershocks surrounding each of these main shocks from the source mod distribution. And in total, I think we had about 6.6 million grid cells when all this was assembled. What we found overall after kind of setting this all up was that a kind of classic version of Coulomb failure stress change resolved on receiver planes parallel to the main shock fault orientation could do kind of somewhat better than random assignment. So this is what's shown here is a depth slice at 12.5 kilometers depth for the 2005 Kashmir earthquake, a magnitude 7.6 oblique thrust event in Pakistan. And the red to white color scale are the calculated Coulomb failure stress changes at this depth slice. And the black squares are the locations of the grid cells that generated one or more aftershocks in the year after the earthquake. The fault is in yellow. The corresponding ROC curve across all depths is shown over here. And what's sort of interesting, so the cutoff threshold, this is plotted for all cutoff thresholds of the binary classification scheme. And this red dot highlights the cutoff threshold for Coulomb failure stress change of 0.01 MPa. And in general, this is sort of consistent across the entire data set. The cutoff thresholds at which you kind of get the best discriminating ability for Coulomb failure stress change are usually between about 0.01 MPa and 0.03 MPa. So we were interested in seeing if a neural network could find a combination of static elastic stress changes that could do any better than this quantity. And so to do this, we just divided the data set we'd assembled into a training and testing data set. We did this based on distinct main shock to avoid a situation where you had like one Landers slip distribution in training and one in testing. So 75% of distinct main shocks were sent to training and the remainder to testing. And then we trained, again, fully connected networks with features that were just the raw static stress changes at the centroid of each grid cell, and then corresponding labels that were just a 0 or a 1, depending on whether or not that grid cell experienced an aftershock in the year after the earthquake. So once trained, these kinds of binary classifiers, their output is between 0 and 1, and it's often interpreted as sort of a probability-like value. And in general, the neural network seemed to be able to find a combination of static elastic stress changes that did seem to be able to do better than this classic version of Coulomb failure stress change. So this is, again, a depth slice at 12.5 kilometers depth for this neural network. And you can see, based on this ROC curve, that it does seem to do a lot better. The area under the curve for this is, I think, 0.6, and this is 0.86. And this red dot highlights a cutoff threshold of 0.5. Yeah?
How did you select your testing data set? How did you see? You have three categories of data, right? Two categories. One is training, one is evaluating, and the other one is testing data set, as I understood from the systems course. So how did you select between all these data sets? You have 11,000 data points. So how did you select your test data sets?
So we selected them randomly from, so we had 199. We did it based on distinct main shock. So we had 199 different slip distributions and 118 distinct main shocks. So we
you shuffled first your information table, right, randomly.
Yeah. So we shuffled the names of the distinct main shocks, 118 of them, and then took 75% of them randomly to training and the remainder to testing, and then assigned all the relevant slip distributions to each of those. Does that make sense?
What are you training on? The probability of an aftershock?
Yeah.
Meaning, how many were in each cell?
No, so it's actually just a binary thing. We're just, so we have a little bit less information than that. We're just doing, was there an aftershock in the grid cell or not? At least for this, for now.
It says aftershock probability.
Yeah, so it's the probability of that's maybe, I should say, probability of a grid cell generating one or more aftershocks in the year after the earthquake. But that seemed too long. So yeah, so when you're training, you have features, inputs that are just the raw static stress changes along with the 0 or 1, because you know for those examples if they generated one or more aftershocks or not. And then once trained, the neural network sort of outputs a value between 0 and 1 that sort of indicates how likely it is that things.
Oh, I see.
Does that make sense?
The train.
So how to put is aftershock probability at a specific point, or
Yeah, so it's in that grid cell, given the static elastic stress changes, what
so the
probability?
input is also at the point or the grid.
Yeah, the input's in the centroid of each grid cell. So we're just kind of testing this one, we're focused on just aftershock locations and just static elastic stress changes. So we've really isolated sort of a small piece of this. One other metric that I find kind of useful for assessing these binary classification schemes is the precision, where in this case it would be defined as, for a given threshold cutoff, the fraction of grid cells for that threshold cutoff that you would identify as high risk that actually do generate aftershocks. And the precision of both of these classifiers is not very good. The precision associated with 0.01 MPa for Coulomb failure stress change is, I think for this, 2.5% for the Kashmir earthquake versus 7% for the neural network. So the neural network does better in terms of precision, but neither of them is particularly precise. It's just important. I think it's a good metric to keep in mind. This is an example where neither of these classification schemes does quite as well. This is the Chi-Chi earthquake in Taiwan. Again, an oblique thrust event, magnitude 7.7 or 7.6. And I think there were in total about 560 aftershocks in the ISC catalog for this event. And you can see the area under the curve for Coulomb failure stress change is, I think, 0.57 compared to 0.76 for the neural network. And then the Kobe earthquake in Japan. There were only 40 aftershocks in the ISC catalog for this event, but for the aftershocks that do exist in the catalog, the neural network seems to perform better than Coulomb failure stress change. And this kind of performance difference is consistent across the entire testing data set. So each of these gray curves is the ROC curve for a different slip distribution in the testing data set. So I think there are 58 slip distributions in total in the testing data set and 31 distinct main shocks. And the area, this blue curve is the merged ROC curve across all of the different slip distributions for Coulomb failure stress change in the neural network. This red dot highlights a cutoff threshold of 0.01 MPa and again 0.5 for the neural network. So the overall precision on this testing data set of Coulomb failure stress change was at this cutoff threshold 3% versus 6%. So again, the neural network performs, I guess, double as well in terms of precision, but both numbers are very low. The kind of last thing that we were interested in looking at this with this was kind of, we were wondering if we could figure out something about what the neural network found important or what it learned was important in discriminating between these two types of grid cells. And it was kind of daunting to think about doing this kind of interpretation with the very complex slip distributions in the source mod catalog. And so what we decided to do is we decided to look at what the neural network would output for synthetic idealized earthquakes. So this is the neural network output for a synthetic idealized strike slip earthquake. And I think a magnitude about a 7 event. So the yellow would be where the neural network would forecast the highest probabilities of aftershocks. So in order to try to interpret this, we just compared this spatial pattern to the spatial patterns of a suite of different static elastic stress metrics. I think we compared to 40 in total. So everything from just the plano distance to the fault, to maximum shear stress change, to a suite of different versions of Coulomb failure stress change, absolute value and not, all the invariants of the stress tensor, both deviatoric and full. And what we found was really pretty surprising to us. 98% of the variance in this neural network output could be explained by the von Mises yield criteria, which is a scaled version of the second invariant of the deviatoric stress tensor. It's also very highly correlated with the maximum shear stress change. And I immediately, when we saw this, I went to Google Scholar and looked up had anyone ever used this quantity for earthquake-related things. And there's a paper by Kagan and Jackson in 1998 in which they specifically propose the second invariant of the deviatoric stress tensor as being useful for explaining aftershocks, I think in California. But to us, this suggested that we've only looked at aftershock locations and static stress changes here. But going forward, this sort of suggested to us that these kinds of approaches, they might be useful in identifying specific physical phenomena or specific physical quantities that might warrant further investigation. And this aftershock forecasting in general is, in a lot of ways, very well suited for machine learning because there are a lot of data, and there are also a lot of different physical phenomena that may affect aftershock behavior. And machine learning can really shine at, discovering complex relationships between inputs and outputs. So we're excited to see kind of where this can go going forward. I should say, we did a few tests just to make sure that this seemed robust. Two of the things that we did were to kind of address concerns that because we had multiple slip distributions from the same main shock in the training set and the testing data set in some cases, we did this kind of ensemble approach where we took 10 realizations of the training data set and the testing data set, with each realization only having one randomly selected slip distribution from each main shock. And we got results that were really very similar in terms of overall pattern and performance. And we also tried variable depth limits. So we incorporated only depths that were, 5 kilometers, up to 5 kilometers beneath the deepest depth of the slip distribution. And again, very similar results. What we've been working on most recently, this is all very preliminary, but we've been sort of looking more at aftershock density patterns, magnitude patterns, timing patterns. And aftershock densities don't seem very interesting so far, just more aftershocks happen near the fault. But the magnitudes might be kind of intriguing. You can see we've done relative magnitudes, so it seems like the neural network once trained predicts highest probabilities of small aftershocks close to the fault, but farther away, but slightly higher probabilities of the larger aftershocks farther away from the earthquake. And that's somewhat consistent with a paper by Van der Elst and Shaw, I think, that found that larger aftershocks tend to take place farther away. And we've also isolated just strike-slip faults because there's a lot of, especially in the 1990s, there was a lot of discussion of whether or not there's some bias in the literature about focusing just on strike-slip faults. And so we were interested to see if we get different patterns if we just look at strike-slip faults. And so this is sort of what we get if we train only over strike-slip faults, and this neural network performs slightly better on strike-slip earthquakes and looks very different. So this is sort of what we're working on now, but all very preliminary. So yeah, with that, I'm happy to take any questions. I'll just leave up the conclusions.
Yeah, you can take over questions. Yeah. So I think we have time for like a couple of quick questions. So. Hi, Viva.
Have you given any thought to applying this to including foreshock sequences and trying to kind of zero in on the location of the main shock?
Yeah, I mean, we've definitely been thinking about things like that. That'll be really, and we've also just also looked at seismicity rate changes before and after, because I think that's really the thing you want to look at for whether or not static stress changes have any influence. But definitely, I mean, that's the big challenge.
Yeah, and it would be interesting to see if they're governed by sort of similar relationships or not.
Yeah, I think it'd be cool.
So I have, like for a large earthquake, so like either greater than 7 or other certain magnitude, they may have really large aftershocks. Those large aftershocks may kind of act as a secondary main shock and trigger it. And what I'm thinking is the dynamic triggering system and also the nonlinear trigger between main shock and aftershock. And so do you consider this a complexity?
No, we don't. We focus totally on static elastic stress changes for now, to sort of isolate this one part of the problem. But definitely the cool thing about these approaches is that you could incorporate dynamic stress changes, poroelastic, viscoelastic, existing locations of geologic structures. Like, you could just incorporate all that kind of information.
For specific earthquakes, there are usually several dynamical inversion models. So, and sometimes they're not usually very similar to each other. So how did you choose them?
Wait, can you say that again? Sorry, I didn't quite understand.
I mean, for a large earthquake, there are usually like several or tens of different dynamical inversion models, and they are not very similar to each other. So how did you choose them?
We just used all of them from the source mod catalog. We used all the available ones that we could.
Okay.
So that was a brute force.
So that's similar to my question about the uncertainty quantification for AI. So we can talk after your talk. So you should finish your lunch first and bring back your babies. And so for all the audiences, you have more questions or you want to stay on to discuss with Phoebe, you can just stay here. We can just chat casually for 1 hour. Yeah. Okay, thank you for coming.